1 afternoon session. I'm Raya Hadsel. I'm going to be the session chair. The first spotlight is going to be on robust subspace estimation in a stream, and it will be presented by Roe Levin.
Hello, welcome to my talk. My name is Roe. I'll be talking about robust subspace estimation in a stream. This is joint work with Nish Sevikari and David Woodruff. All of us are from CMU. So I have about enough time to tell you what the title means. So what's the problem we're solving? This is the problem we're not solving. We're given a set of n data points, okay, that live in RD, and a target dimension k. And the goal is to output a k-dimensional subspace of RD, such that we minimize this sum of squared distances of each point to the subspace, okay? And the notion of distance we're using is the standard Euclidean distance. So this is a classic problem, and we're going to study one robust version of this problem. So we're going to replace the squared term with just the distance. So we're minimizing the sum of distances to our subspace. And what does in a stream mean? It means that we never see the data like all up front. We're given the data points one by one in a stream. And the hard part here is to solve the problem in sublinear space. Okay? And in fact, our algorithm is going to work in what's called the general turnstile streaming model. So we actually don't even need to see the points one by one. We're OK with arbitrary like entry-wise additions and subtractions to those data points. So pictorially, it looks something like this. And we're going to write this objective as this low-rank approximation problem with this thing I'm calling the 2-1 norm. This weird thing. It's easy to work out. It would take you about a minute, but basically it's this norm means that you take a matrix and you take the L2 norm of each row, and then you sum these. Okay, so you can basically just express this problem this way. So in 2015, Clarkson and Woodruff showed that the offline version of this problem is NP hard to approximate to within a 1 plus 1 over poly d factor. Okay? So surprisingly, this is a very hard problem. And particularly, this implies if you want a 1 plus epsilon approximation algorithm, you can't hope for a polytime algorithm. So on the flip side, they do give a 1 plus epsilon approximation algorithm. Okay, and the key here is that they spend time exponential in a polynomial in k over epsilon. Okay, so this is still a big win because it's not exponential in n or d. So n is the number of points and d is the dimension. Okay, and other than this exponential term, the leading order term is n and z of a, which means number of non-zero entries of a. Okay, so this is a very, very fast algorithm. Okay, so what do? We show that there is a 1 plus epsilon approximation algorithm to the same problem with the following guarantees. It runs in the turnstile streaming model with sublinear space. And furthermore, if you run it offline, which is kind of the only way it makes sense to make a time comparison, it's actually the same as the Clarkson-Woodruff algorithm up to the leading order terms. So in the minute or so I have left, let me try to give you a very sketchy version of how we do this. So we're given this problem, and we don't know what to do about this weird norm. We don't know how to solve this minimization problem. So what we're going to do is we're going to reduce the problem to a different problem, hopefully with smaller dimensions. Okay? So we're going to somehow pick these y and z that are functions of a. Believe me that you can brute force the solution in time that's exponential in the dimension. This is not straightforward, but one can show this. So now I claim if we show three things, we'll have shown our claim. The first is that the solution below is indeed a 1 plus epsilon approximate solution to the first problem. The second is that f1 and f2, these functions, are what's called oblivious linear sketches, which means that they're linear functions, and so they're matrices, and the entries of this matrix does not depend on A. Okay, which means that we can compute these matrices without even seeing A in the first place, and then exploit linearity. As every incoming data point comes in, we apply this matrix to that data point and add it to what we've seen before. Okay? And finally, if the dimensions of y and z are small, so polynomial in k over epsilon, then we indeed get this time that's exponential in polynomial in poly k over epsilon. Okay, so just to wrap up, we have some experiments on both synthetic data, so we can construct examples where our algorithm does arbitrarily better than the first thing you would try, which is the like truncated SVD, as well as some real-world data. So thanks, that's just about my time. Thank you. Oh, come see me at the poster.
Just 2 notes before we go on. First of all, we can't have anybody standing at the sides, so if you're standing, just find a seat, please, for fire code. And secondly, would all speakers for the session please make sure that you've come forward and are sitting in the front row, just to avoid problems later. The next talk is on efficient non-myopic batch active search, which will be presented by Shali Jiang.
Hello, everyone. My name is Shali Jiang. Today I'm going to talk about efficient non-myopic batch active search. This is a joint work with Gustavo, Matt, Ben, and Roman. Many real problems involve searching for valuable items from a large pool of candidates in an iterative fashion. Drug and materials discovery are 2 typical examples. We formulate this problem as active search. Suppose there is a big pool of unlabeled points. A few of them are positive, and most of them are negative, and you want to identify the positives. Now suppose you have an inference model that gives you the probability of each point being positive. Now given this information, you can select the points and query an oracle. Is it positive? Then oracle will answer your query with a certain cost. Now based on this new observation, you can update your model and repeat this process. Your goal is to identify as many positives as possible in a given number of queries. The key question we study here is how to select a point. Our previous work studied the case of selecting 1 point at a time. However, in many real applications, we can often query multiple points in parallel. So in this work, we study how to select a batch of points. The most straightforward policy one might think of is greedy. That is, always choose the points with highest probabilities. This is optimal in terms of maximizing the expected number of positives in this batch, and it's computationally efficient. However, it's myopic, ignoring what could happen in the future. How can we do better? We propose non-myopic batch policies. That is, we consider not only how much we get from this batch, but also the expected future reward if we choose this batch now. However, this policy is computationally intractable, since we have to recursively simulate a search tree of size exponential in the remaining budget. We adapt an idea developed in our previous work and compute an approximate expectation by assuming conditional independence after this batch. This is efficient in sequential setting. However, in batch setting, it becomes combinatorial search. We propose 2 approaches to tackle this challenge: greedy maximization and sequential simulation. Greedy maximization is a common practice for maximizing set function. We'll briefly talk about the second one, sequential simulation. The idea is simple. We simply simulate a sequential policy by selecting points 1 by 1 to add in the batch. And we use fictional oracle to fake the label and update the model based on the fake label and selecting the next one. The key question here is, how do we assume the label? For example, you can sample a label. You can use a most likely label or always assume positive or negative. Interestingly, we find always assuming negative performs the best. And this is because assuming negative creates repulsion. And this repulsion encourages diversity of this batch and hence better exploration of the search space. We find that our non-myopic policy improves over myopic ones by a large margin and demonstrates nice exploration-exploitation behavior. Batching is certainly more efficient, but is that something we are compromising? Suppose we can query 20 points. We can either query points 1 by 1 for 20 iterations, or say we can query 5 points at a time for 4 iterations, which is much more efficient. However, in the latter case, the points are often chosen in a less adaptive fashion, which could lead to worse performance. But how much worse? We proved that the performance ratio between optimal sequential and batch policies is at least linear in batch size. And this theoretical result is found to match our empirical results. And this insight could help us choose the batch size in cases where we have many options. Thank you for your attention, and welcome to stop by our poster 131 in level 5. Thank you.
The next talk is on interactive structure learning with structural query by committee, presented by Christopher Tosh.
Thank you. This is joint work with Sanjoy Dasgupta at UCSD on interactive learning. So why do we want to do interactive learning? Well, there are a few issues that arise in traditional non-interactive settings. For example, in supervised learning, it's often the case that collecting unlabeled data is very cheap, but collecting the labels associated with that data is orders of magnitude more expensive. So labeling an entire data set is prohibitively expensive in some domains. In unsupervised learning, it's often the case that choosing our initial model to fit is not entirely clear. And even when we do choose a model to fit and we get a reasonable fit, it's not clear how to correct obvious mistakes in that model without throwing everything out and starting over. So previous works have tried to address these problems in each of these settings. In active learning, people have tried to approach the supervised learning setting, introducing interaction into there. And there have been interactive protocols for clustering that have been introduced. But there are a few problems with these previous works. So the first one is that typically these have been studied in isolation, which means that whenever you want to address a new setting, you have to come up with your new interactive protocol and your new algorithm, and that can be difficult to do. Additionally, most of these settings have required the user to answer every single question that's put in front of them, even when they're unsure, which can lead to noisy feedback. So in this work, we introduced this generic interactive learning protocol called interactive structure learning. And it proceeds as follows. The learner maintains some sort of model fit, and at each round, it presents the user with some data points, and this model fit to that subset of data points. And then the user looks at this substructure and provides some sort of correction to it. If there is one, or says no, everything looks good. So for example, in a clustering, it would look at this subclustering and say, no, these 2 points should not be clustered together. So there are a couple nice properties of this protocol. So the first one is that providing these snapshots provides context and hopefully elicits more accurate feedback. Additionally, by only requiring the user to provide partial correction, we also should hope to elicit more confident responses from the users. Finally, this framework is extremely generic. So it actually generalizes active learning and interactive clustering among other tasks. So addressing things at the interactive structure learning level actually leads to efficient algorithms in all of these settings as well. So formally, the approach that we take in this paper is to maintain a posterior distribution over structures. And at each round, we select some subset, show it to the user along with some structure drawn from our posterior distribution. We get some feedback from the user, and then for every structure, we update our posterior by downweighting those that are inconsistent with this feedback. And by only downweighting, we allow the user to provide possibly noisy responses. So the main algorithmic question that remains is, how do you go about choosing this subset? And in this work, we consider a generalization of the query by committee rule, which we call structural query by committee. And it has some properties associated. For example, we can show that under fairly minimal assumptions, if the user, under the user's feedback, that this algorithm is consistent. And under stronger assumptions, we can actually quantify this convergence rate. We also have some Other results in the paper, for example, we consider a broader class of posterior updates to allow for efficient sampling from the posterior. And then we also look at kernelizing this querying rule, and we also present some simulations. If you're interested in learning more, please come see our poster, number 130, upstairs tonight.
Great. The next spotlight is contour location via entropy reduction, leveraging multiple information sources, presented by Alexander Marquez.
Thank you for the introduction. So I'm Alex Marquez. Today I'm going to talk about locating contours of functions leveraging multiple information sources. So this was developed with Remy Lam, former MIT, now at DeepMind, and Professor Karen Wilcox from UT Austin. So our goal here is to construct a classifier, but instead of having a discrete set of labels, we actually have a continuous function, and some specific contour of this function divides the domain into different classes. So for instance, here we have a function that characterizes the stability of a dynamical system. So the zero contour of this function divides the domain into regions where the behavior is stable and unstable. The challenge here is that normally obtaining this contour, an estimate of this contour, requires many function evaluations. And doing these evaluations in some problems is very expensive. However, in many cases, we also have access to other sources of information that provide relatively cheap information about the system in the form of some biased estimate of the expensive function. So the question that we wanted to answer here is how can we leverage all of these information sources to produce an accurate classifier at relatively low cost? And our answer to this question is an active learning algorithm that uses a Gaussian process surrogate to fit data coming from all different sources simultaneously, and that learns the correlations between the different sources. So we use this information to select new evaluations, so where to make new evaluations and which model to evaluate next. So here I'm going to show an example of comparison of the performance of this new algorithm, this multi-information source algorithm, which is shown here on the right. So we have here three information sources, IS0, IS1, and IS2. And we're going to compare it to a standard active learning algorithm with a single information source, which is shown on the left. So I'm going to show the estimates of both algorithms at the same cost. And we start both algorithms with 10 random samples. So at the time that it takes to have a single IS0 evaluation for the single fidelity, single information source algorithm, the multi-information source algorithm decides that it's much more informative to have several evaluations of the cheaper information sources, and uses that information to have a better estimate of the contour that we are trying to locate. And just at the cost of one more IS0 evaluation, we basically, the multi-fidelity, multi-information source algorithm has basically nailed the estimate of the contour, whereas the single information source algorithm is still kind of struggling to have a good estimate. And as we progress the evaluations, what we see is that the multi-information source algorithm is basically using the cheap information sources to explore the domain in an intelligent fashion, and just using a limited number of IS0 evaluations to pinpoint the accuracy of the estimate. Whereas the single information source algorithm doesn't have a choice. It has to do some sort of exploration of the domain using only expensive IS0 evaluations. So eventually we'll get there, but it will take a much longer time to have a good estimate. So the contributions of this paper are threefold. So the first one is we introduced this concept of contour entropy, which is a rigorous measure of the uncertainty about the location of the zero contour of a function approximated by statistical surrogate. The second contribution is a decision mechanism in which we use our Gaussian process surrogate as a generative model to estimate an expected reduction in this contour entropy for a given evaluation. So we use that to estimate what is the evaluation that is going to lead to the most reduction in contour entropy per computational cost. So we select both where in the parameter space to make the evaluation and which model to evaluate it. And then we put it all together in the algorithm Clover, which combines data from multiple information sources to locate contours of expensive functions at a relatively low cost. So with that, I'd like to invite everyone to come to the poster session and talk to us. This is poster 99. Thank you.
Hello. Next, we have the first oral of the session. The title of the paper is Sample Efficient Reinforcement Learning with Stochastic Ensemble Value Expansion. The authors are Jacob Buckman, Danijar Hafner, George Tucker, Eugene Brevdo, and Hong-Lak Lee. It'll be presented by Jacob Buckman.
Thank you. Good afternoon, everybody. On behalf of my collaborators at Google Brain, I'm proud to present our work on sample-efficient reinforcement learning with stochastic ensemble value expansion. Stochastic ensemble value expansion, which we abbreviate as STEVE, is an approach to deep reinforcement learning that merges model-based and model-free techniques. We use ensembles of neural networks to maintain uncertainty estimates for both the Q function and dynamics model, and use model-based reinforcement learning only when we are confident in the predictions of our dynamics model. We evaluate on a variety of continuous control tasks and find that STEVE is able to match or surpass the performance of model-free approaches, even in complex environments. First, some background. Our algorithm is based on DDPG, so we have a neural network Q function approximator, parameterized by theta, to predict the expected return for a given state action pair, as well as a policy function pi, parameterized by phi, to predict the action which maximizes Q in any given state. The Q function is learned in the standard way. When interacting with the environment, we maintain a replay buffer of transitions. So each transition contains a state S, the action A taken in that state, and the resulting reward R and next state S prime. We update our Q function by minimizing the squared error between our initial guess based on the state and action and our updated guess incorporating future information. This is known as the TD target. Our work also builds upon model-based reinforcement learning. In model-based RL, we learn a dynamics model, which predicts how the environment will respond when we take an action. In our case, we learn both a transition function, T, and a reward function, R, each of which are, again, neural network function approximators. There's a large amount of literature on model-based reinforcement learning with many strategies for using this dynamics model to accelerate learning. In our work, we focus specifically on using the model to improve our target. Specifically, we build on recent work on model value expansion. So the idea of how that works is, starting from the next state, S prime, shown here in green, we use our policy to predict actions, and then use our dynamics model to predict rewards and future states, essentially rolling out our model into the future. This gives rise to a new target, which is simply an n-step Q-learning target on our rollout. We refer to this as the MVE target, which is subscripted by some rollout horizon h, corresponding to the number of steps of rollout. In this case, we have h equals 3. Comparing this to our TD target, it's easy to see why this might help. The discount factor applied to the Q function for the MVE target is gamma raised to the power of h plus 1, in contrast to the TD target, which is just gamma. The contraction rate of the Q function is equal to this discount factor, so if the reward and state predictions are accurate, then we expect that the extra discounting will lead to faster convergence. However, dynamics models are not without their own issues. The error of the learned model puts an upper bound on the performance of the learned policy, because even a policy that performs perfectly in an incorrect model of the environment could have poor performance in the real environment. Additionally, this is somewhat likely to happen because the policy learner is in some sense adversarial to the model, in that it will actively search out model errors if those model errors correspond to the reward being overestimated. And finally, even if our model is very accurate, multiple steps of model rollout could cause initially small errors to compound into large errors that then cause the first two issues to arise. So, going back to our comparison of these two targets, we can see that there are many opportunities for model errors to affect the MVE target, but none in the case of the TD target, which of course makes sense because standard TD learning is model-free. So hopefully that gives everyone a good sense of the factors at play here. Model-based approaches can improve the sample efficiency of DQN, but using a learned model comes with many issues and can hamper performance. In model value expansion, this trade-off is clear. More steps of rollout increases the contraction factor, but introduces opportunities for model error. To see this in action, here's a simple value approximation task in a tabular environment. For this environment, we know the true value function for each state, so we can compute the error in closed form after each update. This green curve shows how regular, model-free TD learning gradually converges to the correct Q function, taking about 20,000 time steps. In red, we now see what happens if we do model value expansion instead, using an Oracle dynamics model, one that perfectly matches the dynamics of the true environment. We can see it converges far more quickly. However, what if we don't have access to a perfect dynamics model? What if we only have access to a noisy one? This dotted red line shows what happens. Even with a small amount of noise, the model-based approach not only performs worse than the model-free, but actually completely fails to converge at all. Our work on Steve is motivated by a desire to fix this issue. We've seen that each step of model value expansion comes with a trade-off of sorts. We want to compute a target, T Steve, that reliably balances this trade-off to have a lower overall error than either the TD target or the MVE target. The intuition for how we want to do this is we compute many MVE targets with different rollout horizons and choose a length of rollout that doesn't make significant model errors. In order to figure out what length to choose, we estimate our uncertainty and ignore high uncertainty targets. Our approach assumes deterministic environments and policies, and we leave stochastic environments and policies for future work. So these MVE targets at many different horizons we refer to as candidate targets. First, notice that the TD target is actually equivalent to the MVE target with a rollout horizon of 0. We can then get our other candidate targets by extending this for each horizon up to some maximum, rolling out one step at a time. Written as equations, these simply correspond to the various n-step targets. Now, in order to compare the goodness of these targets, we need to additionally maintain uncertainty estimates. We use the bootstrap ensemble technique, which involves replacing each neural network with an ensemble of neural networks. For example, in this particular instance, we replace our transition functions with an ensemble of size 2. The two transitions functions are represented here as blue and cyan. We initialize each member of each ensemble randomly and train them on different independently sampled mini-batches at each update. We can then sample many different combinations of these functions to get different estimates of the MVE target. So let's say we wanted to compute the 2-horizon MVE target and its uncertainty. We would start by sampling a neural network from each of our ensembles, and then just compute the target as regular. In this case, we sampled dark green, blue T, and orange R. If our ensemble sizes are small, in this case we only have 2 of each, we could exhaustively enumerate the combinations of ensemble members, but in general, what we want to do is resample several more times and get many different estimated values of our 2-horizon target. This procedure is where Steve gets its name. We maintain various ensembles and do value expansion by stochastically selecting a new subset each time. Once we've taken many samples, we can use the mean as our target, and the variance gives us an estimate of our uncertainty. Repeating this procedure for each horizon length gives us h+1 candidate targets and their corresponding uncertainties. We want to merge the targets into a single target with minimum expected error. We first decompose the expected error into the bias and variance terms, and in this work we ignore the bias and focus only on minimizing the variance component. If we assume that the candidate targets are independent, it's well known that the minimum variance estimator of several independent estimators can be computed via constrained optimization, resulting in inverse variance weighting. As an aside, we can also include the covariance terms, but computing the target then involves taking a matrix inverse, so it's much slower. We find that it doesn't make a significant difference in performance, so we don't do it in practice. So essentially, as you can see here, our final target for T-Steve is a weighted average of our candidate targets, where the weight of each horizon length is proportional to the inverse of the variance of the predictions at that horizon length. Here's a visualization that should give you some intuition about why and how Steve works. The y-axis of each of these figures represents several updates to the model, maybe multiple samples from a mini-batch or multiple sequential updates. The x-axis corresponds to the rollout horizon used by that respective target. The darker a square is, the more weight is being given to that horizon length. The TD target assigns all of its weight to the 0 horizon rollout at every time step. The MVE target always rolls out all the way, assigning all of its weight to the maximum horizon length. We also could consider simple methods, such as taking the mean across all different horizon lengths, or decaying the weight with TD lambda. These result in slightly more interesting plots, but note that all of these approaches are still consistent across samples. In contrast, Steve produces this interesting patchwork behavior, as it flexibly adjusts its rollout horizon on an example-by-example basis. This additional flexibility is where Steve derives his power. To see this in action, let's bring back that toy problem that we saw earlier. Here, we add on the Steve curves in blue. As you can see, the solid blue line, representing Steve with a perfect world model, converges almost as fast as MVE does. However, the dotted blue line, representing Steve with a noisy dynamics model, now still converges, and in fact, even still converges faster than regular Q-learning. We also evaluate on a number of larger scale continuous control tasks. Note that we are now reporting reward, not loss, so higher is now better. The blue line here is again Steve, while the red and green lines are our model-based baseline, model value expansion, and our model-free baseline, DDPG, respectively. We see that Steve matches or outperforms the baseline on every task. Interestingly, this gap is larger on the more difficult tasks, such as humanoid V1, even though the dynamics of these environments are much more difficult to model. To further investigate whether our algorithm is robust to model errors, we took the most complex environment and ran several versions of Steve with various maximum rollout horizons, visible here as various blue lines, with the darker lines corresponding to longer horizons. We can see that as we increase the rollout horizon, the sample efficiency improves, without the performance degrading. Finally, we also include here in pink a version of Steve that takes into account the covariance. As you can see, the performance is not significantly better or worse, but it was much slower to run, so we used it only for this curve. Speaking of time, computing the Steve target at each time step does take significantly longer than the regular TD target, up to 5 times more. We ran the experiments comparing the wall clock time of these algorithms to determine whether the increased sample efficiency granted by Steve made up for the slower per update speed. We found that Steve either matched or surpassed baselines in terms of wall clock time on tasks that we investigated. To summarize, we introduced Steve, an uncertainty-aware reinforcement learning algorithm. Our technique for merging model-based and model-free approaches leads to high performance and sample-efficient learning. All our code is available online, open source, and please come check out our poster number 167 if you would like to learn more. Thank you.
We have time for a question, if you'd like to come to the microphone. David. You're good.
So the key difference is that Dyna, you're actually doing all of your training in the sort of modeled environment itself, in the simulated environment. And then you're doing one step, you're sort of mixing in one new step of environment interaction per cycle, whereas with these approaches, every single update is computed using both some information from a real transition and some information from a simulated transition.
Are there other questions? So I was wondering, what happens in stochastic environments? Obviously, this won't quite work out of the box, I guess. What do you see as being needed to apply it?
Yeah, so in stochastic environments, our estimates of uncertainty end up merging both the sort of epistemic knowledge-based uncertainty and the aleatoric uncertainty fundamental to the environment. You could wind up with a sort of a rollout horizon that has a large amount of variance in its value, but that's because you had to roll a die on your way there, and that's where the variance comes from. But really, we should be confident in that target because we have high confidence in our knowledge of the distribution of values at that point. So it would actually only require a slight change in the formulation with regarding to how we do that uncertainty approximation. And you would need to take at least 2 samples of each ensemble the same way. But it would be not that significant of a change, but is left for future work.
Okay. Anything else? Yes. Can we turn on the microphones?
Almost none for these tasks. All the sort of simulators are simply feed-forward neural networks of 3 layers that take in the state representation. We do low-dimensional proprioceptive inputs for this, not from pixels, but it just takes in that vector of proprioceptive inputs and the action used, and passes it through feed-forward layers and returns another vector, another state vector. So almost no structure is included in this. Adding an additional structure would likely help, and that's a direction that we'd like to explore in the future.
All right, great. Thank you. Let's thank the speaker again. All right, we now have another 4 spotlights in a row. The first one is policy-conditioned uncertainty sets for robust MDPs, presented by Andrea Tiranzoni.
Hi, everyone. I'm Andrea, and I'll be talking about policy-conditioned uncertainty sets for robust MDPs. This is a joint work with Shangli Chen, Marek Petrik, and Brian Ziebert. So first of all, why do we care about robustness in Markov decision processes? Well, we know that MDPs have been successfully adopted for both modeling and solving complex sequential decision-making problems. One of the main practical complications is that the transition probabilities of these MDPs are often unknown. When these probabilities have to be estimated from limited amounts of data, the resulting estimation errors can have very bad consequences on the optimal policies that we compute. Unfortunately, this is a risk that is not acceptable in critical applications such as robotics or healthcare or finance. In all these cases, we need solutions that are robust in the sense that they provide guarantees on the optimal policies they compute, even in the presence of this uncertainty. In particular, in this work, we consider robust MDPs when we are given a finite amount and a limited amount of sample trajectories from some arbitrary reference policy. Here, the typical approach is to first build an uncertainty set, which is the set of all plausible transition probabilities according to the given data, and then we compute the robust solution as the optimal policy against the worst-case dynamics in these uncertainty sets. There's a problem. It is well known that when no restrictions are posed on the constraints that are used to form these uncertainty sets, the problem easily becomes intractable. Now, there's a form of constraints that allow tractability, and these are the so-called rectangular constraints. The idea is quite simple. We constrain the transition probabilities at each state or each state action pair independently of all the others. Unfortunately, these solutions, the price we have to pay for this tractability is that the resulting solutions are often too conservative to be useful in practice. And the reason why is that, very simply, we are assuming the worst case at each state action pair, which is an event that hardly ever happens in practical applications. Motivated by these limitations, in this work we propose non-rectangular uncertainty sets, which are defined using marginal features of entire state action sequences. So we suppose we're given a feature function that encodes the relationships between states and actions in our decision processes. Then we use feature expectations, so the expected sum of features that some policy achieves while interacting with the decision process, to summarize this interaction. Given these feature expectations, we define 2 forms of uncertainty sets. The first one is the set of all transition probabilities whose feature expectations under the reference policy match those that are measured from the data. The second one is more practical, and it's the set of all transition probabilities whose feature expectations do not deviate too much from the measured ones. Now, it turns out that the resulting robust optimization problem, so once again computing the optimal policy against the worst-case transition probabilities, where now these transition probabilities are forced to match or approximately match the feature expectations, has many interesting properties. First of all, we are now able to constrain whole trajectories rather than focusing on single states or single state action pairs. Thanks to these feature functions, we can now generalize across the state action space, something that is not possible using standard rectangular constraints. Our uncertainty sets are policy conditioned in the sense that whatever suboptimal reference policy we use to collect the data is not just ignored, but its bias is specifically accounted for in the learning process. Most importantly, we show that although a pretty hard subproblem arises from our formulation, we can devise a tractable and convenient algorithm to approximate its solution. And finally, we verify empirically that we indeed get less conservative performance than standard rectangular solutions. And well, if you're interested in knowing the details on how we solve this objective, please meet us at our poster 168 upstairs. Thank you. I made a mess. How do you? Wait a minute.
That's right. All right, the next spotlight is learning convex bounds for linear quadratic control policy synthesis, presented by Jack Umenberger.
Hi, I'm Jack, and I'll be presenting joint work with Thomas Schoen on learning to control unknown dynamical systems. So we're interested in the task of learning to control. That is, if you give us some data from an unknown dynamical system, for example, some pseudo-random excitations of this inverted pendulum, then our goal is to learn to control the system. In this case, the stabilized upright equilibrium position. So in particular, we're interested in controlling linear time-invariant dynamical systems with the goal of finding a static gain state feedback controller to minimize the infinite horizon quadratic cost given Q and R. So when the model parameters A, B, and pi are known, this would just be the standard linear quadratic regulator problem, the solution of which is well known, but we're interested in the case where the system parameters are unknown. So in place of the system parameters, we have access to observations of inputs and states from the unknown true dynamical system. And then given this data, we can form the posterior belief over the model parameters. Then instead of optimizing the cost for fixed parameters, like you might do in LQR, we can optimize over the expected or average cost with respect to this posterior distribution. So this average cost can be difficult to compute, much less optimize. So we employ this Monte Carlo approximation based on samples from the posterior. These samples can be generated using Markov chain Monte Carlo methods, such as Gibbs sampling. And then to optimize the cost function, we form these convex upper bounds on the Monte Carlo approximation, and we proceed with iterative convex optimization. So the main technical contribution of the work is the formation of these convex upper bounds, and the crux of the problem is that our cost function involves these matrix inequalities. So all the terms in red are known, they're either sampled or given in the problem description, and the terms in black, they're our decision variables. And it looks pretty nice, it looks close to being linear, but there's this pesky matrix inverse here in the middle. So we just replace that with a first order linear approximation, and that obviously gives us a linear matrix inequality, which is convex. But more than that, because this linear approximation lower bounds the matrix inverse, it also leads to a smaller feasible set, and it's this smaller feasible set that gives us our convex upper bound. So here we demonstrate the performance of the method stabilizing that inverted pendulum that I showed earlier. So here you can see the proposed method in pink, and recall the proposed method optimizes for the expected cost with respect to the posterior. We compare against some other methods. In green, you have a worst case method. So that's a robust controller that optimizes for the worst model in your data set, from your set, as well as another robust method in orange, which optimizes for the nominal model that you get from least squares. And you can see that the proposed method offers good performance, especially when there's little data available for learning. So if you're interested or would like to know more, just swing by poster 166, and I'd be very happy to talk with you. I believe it's also upstairs. Thanks.
Great. The next spotlight is multi-step greedy policies in online and approximate RL, presented by Jonathan Efroni.
Hey everybody. I'll talk today about our work on multiple-step greedy policies in online and approximate reinforcement learning. The motivation for this work is basically the fact that multiple-step look-at policies in reinforcement learning give state-of-the-art performance, as everybody probably know. And for example, by combining MPC or by using MCDS in reinforcement learning, impressive empirical success has been achieved in the past. although this impressive empirical success, theory on how to combine multiple-step look-ahead policies in reinforcement learning is scarce. In previous works, multiple-step greedy policies were combined in the improvement stage of policy iteration, whereas here we will deal with how to combine these type of policies in online and approximate reinforcement learning. So before I'll discuss about the contributions of this work, let me briefly discuss about what do I mean by multiple-step greedy policies. And we start with the natural age greedy policy. It is basically the optimal first action in an age horizon gamma discounted MDP, with the following total reward, as you can see here. In order to better imagine it, let's think about some tree search problem, such that in each stage we get a gamma discounted reward, and at the leaf we get the value function times gamma to the age. In this tree search problem, we have some optimal trajectory, some optimal path that achieves the maximal reward. And the age greedy policy is simply the first optimal action at the root. Here it's simply left. The kappa greedy policy with respect to VPI is defined by being optimal with respect to all the possible tree depths that we saw earlier, such that they are weighted with some kappa averaging. So it can be understood as being optimal with respect to this painting here. In order to use both the age and kappa greedy policy in online approximate RL, which we want to do here, we need to generalize a basic fact about one-step greedy policies and soft updates. Specifically, that soft update using a one-step greedy policy always improves the current policy. And a bit more formally, for any policy pi, consider the one-step greedy policy pi G1, and we have the following basic result, that the mixture policy of pi and pi G1 is always better than pi for any value of alpha. And this fact is used in a lot of works in online and approximate RL. However, and unfortunately, it does not hold for multiple-step greedy policy, and it holds only if alpha is sufficiently large. And a bit more formally again, consider the age and kappa greedy policy that we saw earlier. The mixture policy with the age greedy policy, with age bigger than 1, is always better if and only if alpha equals to 1. And for the kappa greedy policy, it is better if and only if alpha is bigger than kappa. In light of this negative result, we still wanted to try to give some natural algorithms, some natural solutions to this problem, meaning we wanted to formulate multiple-step greedy policies while still having theoretical guarantees. So in fact, we gave here some 2 timescale online multiple-step policy iteration algorithm that is doing that, and we analyzed approximate multiple-step policy iteration methods as well. However, we do believe that it is an open and relevant problem to explore what other variations we can do in light of the negative results that we saw earlier. So to summarize, there is an important difference between multiple-step and one-step greedy policies. And also, multiple-step policy iteration in the approximate case has some theoretical benefits as well that I did not discuss in this talk here, and you're welcome to the poster to further discussion. Thank you.
That's a cute meme. Oop. Not sure what it is, but it's cute. All right, the next spotlight is deep RL in a handful of trials using probabilistic dynamics models, presented by Kirtland Chua.
Hi everyone, I'm Kirtland, and I'll be presenting deep reinforcement learning in a handful of trials using probabilistic dynamics models. This has been joint work with Roberto Calandra, Rowan McAllister, and Professor Sergey Levin. Deep reinforcement learning has been successfully applied to many domains, but many current methods often require a significant amount of data to learn tasks well. And so this is an issue in most real-world scenarios because oftentimes we are constrained by resources as well as factors such as wear and tear. And so how can we speed this up? So one prior approach is something called model-based reinforcement learning, where we have the agent learn a predictive model of the dynamics of the world, which it can then use to plan its own actions. And the key idea here is that by leveraging more supervision from our interactions with the environment, we hope that the agent would learn faster. But how well does this actually work? So here we have a model-based method in orange, a model-free method in purple, and the y-axis represents the performance on the half-cheetah task. And so we can see that the model-based method indeed learns quickly compared to the model-free method. However, in the long run, the model-free method eventually outperforms the model-based method, which plateaus earlier on. And so how can we have methods that are able to match the asymptotic performance of model-free methods while having the data efficiency of model-based methods? Let's look at what prior methods have done. So in prior methods, we have a neural network which takes in the current state in action and gives a point prediction of the next state. And so to illustrate the issue, let's consider a toy function and assume that we have samples as well as a neural network that approximates using these samples. So we can see that the neural network is accurate close to the training data and is inaccurate far from training data. And the issue here is that the agent does not know where these regions are, and in the reinforcement learning setting, the agent will have to constantly see states it hasn't seen before in the process of learning. So we modified the model so that it can incorporate two kinds of uncertainty. So the first kind is noise in the data, which we modeled by having the neural network output a distribution over the next state. This allows the agent to plan even in the presence of noise in the environment. The second kind of uncertainty is uncertainty in the model itself, which we captured by having an ensemble of neural network models. And so we can see that the models generally agree close to the training points, while they disagree far away from training data. And so we can take this disagreement as a measure of the uncertainty in the model itself. But how do we actually incorporate these estimates into planning? So the method we use is something called trajectory sampling. And the idea is that given that the agent is currently in a particular state, what we can do is, given an action sequence, we can simply have each network in the ensemble give its own prediction of the resulting trajectory. And so, for example, in this case, we have a particular action, so each network gives a distribution over the next state. And so we sample from this distribution, and we perform this prediction recursively. So we get new distributions, we sample again, and then we sample once more. And this then gives us a bunch of samples of the possible trajectories as predicted by the model. And so how well does our method perform? So here we have our method in blue, the state-of-the-art and model-free methods in brown, and a prior model-based method in orange. And so we can see that our method is able to achieve the asymptotic performance of the model-free algorithm while requiring significantly less data. In fact, we are able to achieve a running gait with the half-cheetah in under 10 minutes of interaction time with the environment, while the model-free algorithm requires several times more data to achieve the same level of performance. And so we called our algorithm PETS, which stands for probabilistic ensembles with trajectory sampling. If you're interested in more details and more experiments, please feel free to check out our paper, as well as our poster at the poster session. Our poster number is number 165. Additionally, we've provided code for all of our experiments. Thank you.
All right, I'm pleased to announce that the next paper has received a Best Paper award. The paper is Non-Delusional Q-Learning and Value Iteration. And the authors are Tyler Liu, Dale Shermans, Craig Boutillier. And here's your award. Congratulations.
All right, thank you very much.
Thank you. And the other two authors are modestly sitting down.
Yeah. All right, hi everyone. I'm Tyler Liu, and today I'll be talking about a new phenomenon which arises in value-based reinforcement learning with function approximation. We call it delusional bias, and it can cause some significant problems for value-based RL. We'll also outline some new algorithms and analysis we've developed to tackle this problem. So we've seen some tremendous success with deep RL in recent years in a variety of domains. And Q-learning has played a crucial role in many of these successes. In fact, it is one of RL's foundational algorithms. But Q-learning with any sort of function approximation, including deep Q-learning, is known to be brittle and can be difficult to make it work well in practice for a variety of reasons. As a result, there's a whole industry devoted to the creation of new algorithms, training techniques, modeling tweaks to address some of these problems. And today I got some even more bad news for you. This may sound surprising, but there are still fundamental issues lurking within value-based RL that have gone unnoticed after all these years. In this work, we present a new type of problem called delusional bias, which arises for two reasons. First, function approximator, we're inherently restricting the class of realizable greedy policies that we can execute. Second, classical algorithms like value iteration and Q-learning perform Bellman backups independently at each state action pair, completely ignoring this policy class restriction. As a result, as we'll see, the interaction of these two aspects can really cause a lot of headaches. But we do have some good news. We developed two new algorithms which completely resolve delusional bias with general optimality guarantees. The first is in the model-based setting, which we call policy class value iteration. The second in the model-free setting, which we call policy class Q-learning. So what is delusional bias? Well, let's start off with a simple observation that doesn't get the attention it deserves within RL. When we learn a Q function using our favorite algorithm, we typically act greedily according to that Q function. This means that with a restricted approximator class, we inherently limit the class of greedy executable policies. To illustrate this, consider this simple MDP, where action D in state 3 gives you small reward, action C randomly transitions you to one of two states, and action A and B gives you either a high or low reward with the parity flipped at the two states. It's easy to see that the optimal policy takes action C, and if you end up in state 1, take A, and if you end up in state 2, take B. This gives you a value of 50. Now suppose that we want to use a linear function approximation, and suppose we have the following featureization. Don't worry about the details, they aren't critical. Well, it turns out that there's no set of parameter values that would assign a higher Q value to action A in state 1 compared to B, and yet at the same time would assign a lower Q value to action A in state 2 compared to B. That is, there's no greedy policy that can execute A in one state and B at the other. This means that all greedy policies have to execute A in both states or B in both states. So it's easy to see here that the optimal greedy policy takes action C and takes action A wherever you end up. This gives a value of 40, which is slightly below that of the optimal policy. So what could go wrong here? Well, suppose we apply Q-learning to this example. And suppose that we sample all the transitions roughly uniformly. Due to the nature of the approximator, if we increase A's value in state 1, we also increase it in state 2. And we push down B's value in both states. And likewise, if we increase B's value in one state, we increase it at the other, and we push down A's value in both states. Well, it's easy to see that this tension causes the stochastic approximation nature of Q-learning to converge to a compromise value for actions A and B with a Q value of 0. This implies that action C also gets a Q value of 0. As a result, Q-learning sees that action D is slightly better with a slightly higher reward, and it converges to a greedy policy that has a value of 1. This is much worse than the greedy optimal policy in the class of representable policies. So what happened here? Well, because the Q backups have no idea whether certain action combinations are jointly feasible, Q-learning is perfectly happy to average together values that are not jointly realizable. In this case, Q-learning deludes itself into thinking that it can average together values of A and B to get a value of 0. As a result, it converges to a greedy policy that is much worse than the optimal greedy policy available in the representable class. So how do we prevent this from happening? Well, notice that whenever we make a max action choice to generate a Q label, we're implicitly making a policy commitment which justifies that Q label. But whenever we make a max action choice at one state, it may conflict with another max action choice at another state. Like in our example, where we cannot do A and B in states 1 and 2. So as a result, in some cases, we may need to compromise and select action choices to generate the Q labels, which are non-maximal. To do this, we need to do two things. First, for each Q value estimate, we need to record the set of policy commitments which justify that Q value. We organize this into what we call information sets, and critically, we need the ability to test whether the policy commitments within an information set is consistent with respect to the greedy policy class. Second, because we don't know a priori which policy commitments might conflict with one another, we need to maintain multiple information sets, each with its own value estimates. So it's best to illustrate this on a running example where we do it in the style of value iteration. So consider the backup in state 2. Normally, we notice that B has a higher value than A, and we associate with state 2 a max value of 50. But because we don't know how the choice of B will interact with max action choices at other states, we also need to record the value of doing A. So in this case, we end up getting two distinct information sets, each with its own different policy commitments and its own Q values. We do a similar backup in state 1, and we get two distinct information sets, each with its own policy commitments and its Q values. Things get interesting when we back up action C for state 3. Normally, we just take an expected value over the successor states, but since we no longer have a single successor state value, we actually need to consider a different possible combination of the information sets or the policy commitments available in states 1 and 2. That is, we actually need to back up entire information sets and not just the Q values. So for example, if we commit to doing A in both states, along with the choice of C in state 3, then we get a new information set with a value of 40. Likewise, if we consider committing to action B in both states, we get a refined information set with a value of negative 40. Now, we might consider doing A in state 1 and B in state 2, but before we even consider that combination, we have to do a feasibility check. And we realize that there's no greedy policy that can execute those combination of action. Therefore, this set must be pruned. Similarly, we can't do B in state 1 and A in state 2, and we must prune this potential information set. And then finally, we do a simple backup for action D. Now we're ready to extract the greedy optimal policy. We do a simple lookup here, and we see that the greedy optimal policy has value 40, given initial state of state 3. And the policy commitments tell us exactly how this greedy policy looks like. We'll notice that at each state, the information sets form a complete partition of the value function parameter space, or equivalently the policy space. Now, you might also be concerned about the proliferation of the information sets, but it turns out that this pruning is exactly what's needed to keep things tractable. Now, it's easy to turn this intuition into an algorithm in a model-based setting, which we call policy class value iteration. And in a model-free setting, we just need to do sample-based backup instead to get policy class Q learning. So what can we say about these algorithms? Well, I'll refer you to the paper for more details. But roughly speaking, we can show the following. First, both PCVI and PCQL converge, and they both converge with respect to the information sets and the Q values contained in those sets. Second, at convergence, we can easily extract the greedy optimal policy and its true value. And furthermore, the information sets and the Q values themselves are non-delusional. And lastly, you might be concerned about the proliferation of the information sets, but the number of them and the number of feasibility checks is actually polynomial in the size of the MBP. They do depend on the VC dimension of the approximator class, but for fixed architecture, we have polytime bounds. As a corollary, for fixed dimensional linear function approximator, PCVI is polytime. So the foundations are pretty solid. But what can we say about its performance in practice? Well, it remains to be seen for larger scale problems. But in some cases, being non-delusional can have a dramatic impact. So we ran our algorithms on some simple grid-world domains, and grid-world can actually be very hard if you have randomly generated features with linear function approximation. So this is a set of results on a 5x5 grid world with sparse rewards at the corners of the grid world. You can see at the top of the plot that the unconstrained tabular Q-learning and value iteration converges to the optimal value estimates. This is as expected. Just below that, we see PCVI and PCQL. With linear functional approximation, we can't expect them to converge to the optimal value estimates, but we see that it very quickly converges to the constrained value estimates. And even quicker, it converges to the greedy optimal policies. By contrast, as we see in the bottom of the plot, by not accounting for delusion, both Q-learning and value iteration with the same approximator class fails miserably. In fact, its induced policies is so bad that they accrue effectively zero reward. So let me summarize by making a couple of key points. First, we believe that delusion is an overlooked but quite important phenomenon that need to be added to the catalog of RL problems. It can cause some significant consequences, including poor value approximation, and as we show in the paper, it can cause a host of other pathological behaviors that are undesirable. We propose new value-based RL algorithms which directly tackle the foundations of this problem, although they are not currently scalable in their current form. But this raises a number of interesting future directions. How do we incorporate concepts like information sets with large-scale Q regression? And we prefer some initial experiments on larger domains with linear functional approximation, and the results look quite promising. But there's still a lot to do here. Second, how prevalent is delusion in practice? Well, based on our preliminary experimental results, as well as arguments with respect to VC dimension on the size of the greedy policy class, we suspect that this is quite prevalent in practice. Third, how do we do efficient feasibility checking with large-scale DNNs? And lastly, we view our methods in some sense as bringing together value and policy-based RL in a very interesting way. And we'd like to explore that connection more deeply as well. So with that, I'll conclude. And if you'd like to chat more about this, please come to my poster session tonight. And yeah, questions.
Thank you. Great. We've got time for a couple of questions. Ian?
Hi. Thanks a lot. Really cool work. But I guess I didn't see the point in, we see that delusion can be a problem, and one solution is to keep track of these information sets. Right. Another solution is to make your function class more flexible. And so that seems like the more obvious solution, and it could actually lead to a better optimal performance. So everybody could speak about that.
Thanks. That's a very great question. So usually we think about this as, you fix your function approximator class ahead of time, right? Whether it's neural networks or something else. And it doesn't matter what function class you consider, the VC dimension is the key indicator. So even if you have a very large neural network, right, the VC dimension is fixed. And depending on how large the problem is, the number of greedy policies is still much less. In fact, polynomial in the size of state space compared to the number of unrestricted mappings from states to actions, which is exponential in the number of states. So, those are two very differing policy classes. So we suspect that, the interaction of the greedy policies as well as the value estimates and the Q backups will still, cause delusion.
I have a question. Wouldn't an actor-critic algorithm resolve this problem automatically? Because then you would be evaluating only policies that can be expressed by the functional approximator. So any actor-critic algorithm, can you comment on that?
Yeah, so I think in general, with on-policy methods, if you're purely on-policy, then you're non-delusional. You're going to be non-delusional. But as soon as you try some type of policy improvement method, you're having to evaluate, what the off-policy or what a potential improving action is. And so when that happens, you need to make sure that the actions you're considering are consistent with respect to your underlying greedy policy class. So there's still that potential for delusion to creep in that case.
But actor-critic algorithms can also be off-policy as well.
Sorry?
I mean, actor-critic algorithms can also be off-policy as well, and I think it would just resolve it automatically.
Well, okay. So maybe we can talk about that more offline. So,
I'm wondering how this compares to like in the context of the problems that we already knew exist with like function approximation, like the deadly triad and stuff, and like I forget what it's called, but there's this two-state MDP, this classic like counterexample to function approximation. So can you like contextualize it against these previously known problems?
Yeah, so that's a great question. So we show in the paper also that divergence is in the example of that two-state MDP as you discussed, can also occur with delusion. So if you remove the delusion, it turns out that the example in the paper, in fact, converges. So there are other issues. For example, bootstrapping, which can cause a host of problems as well, which we don't really address in this work. So some of those aspects about the three deadly triads is kind of orthogonal to what we're doing. But delusion you can think of as sort of a new phenomenon that arises because of the greedy policy class and the queue backups, which don't respect that greedy policy class. And it can cause issues like divergence as well. So, yeah.
Okay, thanks.
Just one quick question while we switch out the computers, and then we'll stop.
Yes, I have a very quick question. Is delusion happens when the optimal policy is realizable by your function approximation, or in that case, we don't have any delusion?
No, it could still happen. So even if the optimal policy is within the class of greedy representable policies, it could still be that your averaging values were corresponding to a combination of actions at particular states, which are not feasible. So you're wasting the capacity of your function approximator to fit those value estimates. So this phenomenon still occurs. It doesn't matter whether the unrestricted optimal policy lies within your greedy class or not. Yeah.
All right, let's thank Tyler again. Thank you. Laptop's down there. Nope. Stop. All right, next we have 4 more spotlight presentations. The first one is bi-level learning of the group lasso structure, presented by Jordan Frekan. No?
Thank you very much. Hello, everyone. So today we present this bi-level approach to estimate the group lasso structure. So we consider the case where we like to predict a vector y from some matrix X. And to do so, we could look for a linear model where we need to find a vector W such as y equal x times W. However, in many cases, only some part of X might be relevant to predict y. So this is why you should prefer a solution W, which is group sparse. And one efficient way to do so is to resort to the group lasso problem. So given some parameter lambda and the prior knowledge of the group structure, the group lasso solution minimizes the sum of 2 terms. The first one measures the discrepancy between y and x times W, and the second one enforces group sparsity. Here you see an example where W hat is made of 5 groups, and only the first and the fourth group are relevant. So there exist many efficient solvers to find W. However, it requires the group structure to be known in advance. And in this work, we propose to estimate the optimal group structure. So to do so, we consider a multitask setting where we have T group lasso problems sharing the same group structure. The groups are encoded by a binary matrix θ1 to θl, and each column of θ encapsulates different groups. For example, the first group is made of the first 18 features, so θ1 is equal to 1 from 1 to 18 and 0 otherwise. On the left side, you can see different regressors. And here, for example, the fourth task only uses the first and the fourth groups. So now we have recast the problem of learning the groups as the problem of learning this binary matrix θ. And to learn θ, we propose a bi-level approach. The lower level problem is made of the T group lasso problems, and the upper level problems permit to select θ according to some criterion. For example, you could choose the validation error. So U of θ will measure how well your solution generalized to new data. However, there are 2 main difficulties. First, W hat is not available in closed form, and also it is not a smooth function of θ. So in order to overcome these 2 issues, we propose an approximate bi-level problem. This problem is very similar to the one before. The only change is that we have replaced W hat by WK, which is the output of a dual algorithm that converged to W hat. And this dual algorithm involves two mappings A and B as follows. First, the dual variable U is updated k times using the mapping A. And then WK is obtained by using the primal dual relationship B. So now the goals are twofold. We would like to find mappings A and B that are smooth in order to smooth the upper level objective UK. And also, we'd like to prove that this approximate bilevel scheme converges to the exact one. So here are the contributions of our paper. First, we have proposed this bilevel scheme to estimate the group lasso structure. And also, we have designed a dual forward-backward algorithm with Brigman distances chosen to make A and B smooth. And also, we have proved that by using this scheme, you can have the convergence of your approximate problem to the exact one in terms of minimum value and in terms of minimizer. So now that UK is a smooth function of theta, we can minimize it by using, for example, the Prox-Saga algorithm, which is a variant of the projected gradient descent. So let's now take a look at some results. Here we would like to estimate theta star that I've shown in the previous slides. And to do so, we let our algorithm estimate and group the features into at most 10 groups. On the left side, you can see the recovered solution. It has currently identified the first 5 groups, and currently identified the next 5 ones as being empty. And on the right side, you can see the impact of this approximate parameter k on the validation error. You can see that for small values of k, you have performance as badly as lasso, and if you increase k, you reach performance close to the group lasso with the oracle groups. For more details, you're welcome to our person 92. Thank you very much.
Great. The next spotlight will be binary classification from positive confidence data, presented by Takashi Ishida.
Hi, everyone. Today I'm going to talk about binary classification from positive confidence data, and this is joint work with Ganyu and Masashi Sugiyama. So if you think about the ordinary binary classification setup, I think you usually have both positive data and negative data, and then you can learn your binary classifier. However, in real-world applications, sometimes you cannot collect any negative data, and you can only collect positive data. So here's our research question. Can we learn a binary classifier from only positive data? This means we do not have any negative data, and we do not even have unlabeled data. This seems like a very difficult task since we do not have any information about our negative distribution. For example, we would not know the direction of the negative distribution compared to the positive distribution, as you can see on the lower figure. So you might be thinking about one-class classification or anomaly detection. These methods describe the positive class by, for example, clustering-related methods. However, they cannot tune the hyperparameters for maximizing the generalization ability, and their aim is not on classifying positive class and the negative class. You also might be thinking about positive unlabeled classification, which use additional unlabeled data from the marginal distribution, as you can see in the lower figure. They also assume that the class prior, PY, is known, and you need this beforehand. This is nice because they aim for classification, but we want to think of the scenario where we don't even have access to the unlabeled data. So what should we do if we only have positive data and we still want to do classification? So here's our main idea. Even if we only have positive data, sometimes we can attach a confidence score to each one of them. So I'll give you a very simple example. Let's say you're trying to think of a dog versus wolf image binary classification problem. Then you'd only have dog images since you only have access to the positive data. But for each of your dogs, maybe you can attach a confidence score. For example, one of your image might be like 95% dog, another one might be like 80% dog. On the right-hand side, we have a figure. The darker colored samples show the ones with high confidence, and the lighter colored ones are the data samples with low confidence. If you're given this kind of situation, I think you could imagine that your binary classifier would be somewhere in the lower right-hand side, as you can see with the black line. So this is intuitive. It might work somehow, but a more important question is, can we really learn a good binary classifier in this way? So the main message in our paper is that if you can equip your positive data with this kind of confidence, which we call positive confidence, you can actually learn a binary classifier with optimal convergence rate. So this was previously impossible when we only had hard-labeled positive samples, but since now we have the extra positive confidence information, and this includes the information of the negative distribution, and conceptually this is allowing us to discriminate between the positive and negative classes, even if we only have positive data. So we call this the positive confidence classification, or PConf classification for short. So let's go into the details a bit more. In binary classification, you usually want to do empirical risk minimization, or ERM. You train a binary classifier G so that the classification risk R is minimized. And the definition of R is given in the first equation here. But there's a big issue here. We do not have data from PXY. You can see in the definition of R that it uses the expectation over PXY. So we cannot simply do ERM. What we do have is we have positive data equipped with confidence. So we have a lot of pairs of Xi and Ri's, and Xi is the positive data drawn from the positive distribution, and Ri is the equipped positive confidence given by the positive posterior, because positive confidence is supposed to show the positiveness of that data sample. So our main contribution in the paper is that we showed that the classification risk can be expressed as the following inside this theorem. Basically, this is showing that you can do ERM with only positive data as long as you equip positive confidence to your positive data samples. And this leads to a theoretically grounded way of objective function design for your PConf classification problem, and you wouldn't need any negative data or even unlabeled data. So to summarize the paper, we proposed a novel setting and algorithm for classification from only positive data equipped with confidence. We established an ERM counterpart to binary classification for this setting. In our paper, we have a lot more work. We have some potential applications. We have experimental results. If you're interested, please come see our poster at number 97. Thank you for your time.
All right, the next spotlight is on fully understanding the hashing trick, and it will be presented by Lior Kema.
Thank you. Hi, so this is John Bork with Kasper Flexen and Kasper Green-Larsen from Aarhus University. I will be talking about feature hashing, which is a key technique for dimensionality reduction in machine learning. So let me first motivate dimensionality reduction by a simple example. So suppose you select a video from your favorite streaming video provider, and the provider wants to recommend you another similar video. So how do we decide which movies are close together? So one common approach is to take the properties of the movies and turn them into feature bit vectors and just compare them using, say, the Euclidean distance. The problem with this is that storing these vectors and comparing them depends linearly on the dimension, which might be very large. So this is exactly the problem that dimensionality reduction comes to solve. Suppose we have a desired approximation ratio and error probability. We want to find a projection from the large feature dimension to a smaller target dimension, such that for every two vectors, the distance between them is preserved approximately with high probability. And in this talk, I will focus on linear projections, which means I can focus on norm-preserving projections. One fundamental result in this field is the Johnstone-Lindenstrass lemma from the 1980s. They achieved exactly this with target dimension that does not depend on the original feature dimension, but only on delta and epsilon. So as I'm standing here, you understand that the story is not over in the 1980s. And the thing is that the projection matrix is very, very sparse. It's very dense, sorry. And therefore, applying the projection is very expensive. But what if we could make A sparser? So in 2009, Weinberger et al. Presented feature hashing. So the basic idea is to take the entries of X and map them into M buckets, and basically shuffle them with random signs, where the projected vector is attained by summing the entries inside each bucket. So this is an example. Quick observation is that this operation is linear, and furthermore, it is as sparse as possible. Every entry of X is touched exactly once by the matrix. maybe a less easy to see observation is that if the target dimension is very large and the mass of X is nicely distributed among its entries, then we can get good guarantees. So what do I mean by the mass of X is distributed nicely? So if you look at this example, this vector has two coordinates which are heavy. And by heavy, I mean that with respect to the total mass of X. Okay, so the way to model this is the ratio between the L infinity norm and the L2 norm of X. In order to hash this vector and maintain its norm, we need these two entries not to collide, not to collide. And this happens with probability 1 over m, which means that in order to get good performance, we need m to be very large. Formally, suppose we have a fixed budget and a fixed room for error. We define by nu the best ratio, the largest ratio, between the L infinity and the L2 norm, such that for vectors attaining this ratio, we get good guarantees from feature hashing. So evaluating this value nu was actually an open problem since the original feature hashing paper in 2009. We resolved this problem by presenting tight bounds on nu. What we show is that if m is too small, then basically we can not give any guarantee. Feature hashing does not give any guarantees. If m is large enough, then we can give guarantees to any sort of vector, and embrace yourself. So if m is between these values, then this is the correct asymptotic bound, and this is tight, so this is the right expression, however nice it is. What perhaps is missing from the theory is the constant hiding within this theta, and we accompany our theory with experimental results that show that actually this constant is very close to 1, meaning that this formula very well predicts the performance of feature hashing in practice. So if you want to know more, you can approach me or Casper offline or come see us at the poster. Thank you.
All right, last spotlight is support recovery for orthogonal matching pursuit, upper and lower bounds. The presenter is Raghav Somani.
Hello everyone, this is Raghav Somani from MSR India, and this is a joint work with Chirag Gupta at CMU, Dr. Prateek Jain and Dr. Praneeth Netrapalli at Microsoft Research Labs India. In this work, we study a simple and classical algorithm, orthogonal matching pursuit, which is very popular in the domain of compressed sensing and sparse regression. So, given a matrix A with n samples each of d dimension and an observation vector of length y, the goal is to find a sparse vector x bar, which minimizes the least squares objective. This problem is NP-hard in general, so we study it under the assumption of restricted strong convexity, RSC, which is one of the most classical and most tractable assumptions in the literature. In the standard optimization setting, the fundamental quantity that captures the hardness of the problem is called the condition number, kappa, which is defined as the ratio of smoothness and strong convexity of the objective function. Similarly, for sparse optimization, there is a restricted notion of condition number denoted by kappa tilde, which is defined as a ratio of restricted smoothness and restricted strong convexity of the objective function. We work under the model where the observation vector y is equal to the product of the measurement matrix A and an S star sparse vector x bar, along with some added noise eta. We just require some deterministic conditions on eta to hold, and in general, sub-Gaussian noise also satisfies those conditions. The goal of the problem are to bound the generalization error, also known as the excess risk. Here, the samples in A are IID sampled from some distribution. And to recover the true support of x bar, ideally we would like to find a small support which covers the true support of x bar. We study sparse linear regression under the RSC assumption for an algorithm, orthogonal matching pursuit. Orthogonal matching pursuit is an incremental and greedy algorithm. It is very popular and easy to implement, and is also widely studied in the literature. The known bounds for sparse regression algorithms had large gap in their upper and lower bounds for the generalization error. The known upper bounds were proportional to square of condition number, whereas the known lower bound held conditionally for polynomial time algorithms and proportional to condition number. In this work, we show that the generalization error bound for OMP is in fact kappa tilde log kappa tilde, and we show an unconditional lower bound for OMP. We also provide results for the support recovery guarantees for OMP, along with providing its lower bound. The known results on support recovery for sparse regression algorithms require a support expansion level proportional to kappa tilde square. In this work, we show that OMP can achieve support recovery in only kappa tilde log kappa tilde times S star iterations. Here we would like to discuss a key idea of the work. We show that if after a reasonable number of iterations, if there is any support unrecovered, then there is a large additive decrease in the function value. And because the function is non-negative, in fact, we can show that the function can be properly lower bounded by a positive quantity. Support recovery will happen very soon. And one can easily show that support recovery with a small support implies small generalization error. Thank you. We hope to meet you at our poster session. Our poster number is 63.
Okay. That's it for the session. That's it for the session.